Hello everyone, Assalamu alaikum. This is the tutorial for MT101 chapter 6. It's all about the applications of definite integral, and we will look at some questions. Definitely we won't go into the theory because that has already been discussed in the lectures. This is just for the practice and to give you an idea about the questions from the previous exams. I picked up a few questions from the past papers. For example, this is the first question that I chose. uh, this is from fall 2021, and this is a bit interesting. Let's solve this one. Okay, so you have been given a region that has been bounded by the curves. It is always easier to solve the question like this if you plot it already. If you know the plot, please go for it. I would highly recommend that. So let's talk about the solution. We know that the graph for under root of y looks something like this. So that is y equals to positive under root of x. And for the negative part, we can have something like this, y equals to minus under root of x. So the graph of 1 over under root x looks like this. It goes like it fades away, y equals to minus 1 over under root x. And similarly, its mirror image about the x-axis, y equals to minus x. So the graph that we are looking for is 4 over under root x. So everything will be multiplied by 4 and that's it. Nothing else changes. The shape of the graph and everything will be the same. Sorry. So it will be something like this. And this one. So we have been given that there are lines x equals to 1. Let's say this is 1. So it's not up to the scale, but we will try to be as accurate as possible. So this is x equals to 4. Here, this is the upper bound. This is the lower bound for our surface for for our region, I would say. And this region, which is now bounded by the lines x equals to 1, x equals to 4, this has been revolved about the x-axis. This is our x-axis. This is our y-axis. Sorry. Let's make a mirror image. So we will have something like this here, and then similarly something like this. Let's say this is x equals to 1, and this will somewhat x equals to 4. So if we revolve this about the y-axis, we're gonna get some solid which is hollow from the inside. Okay, and all of this region and all of this region, and that's all. We need to find the volume of this solid. At the moment, we don't know what method would be appropriate, and it's not given in the mentioned in the question that what method should you use. So we should try like different things. First, I'm gonna go with the method of discs. So if you look for the washer method, we can see that this then. Let me choose another color for this one so that is more visible. Let's go for the blue one. Okay. So if you look at closely, this looks like a washer. A washer is solid like this, which is hollow from the inside, like a donut. And then we will have something like this. I'm sorry about the asymmetry on the both side, but you will have some idea that it looks like a washer. So it is going around like this, and it is a washer hollow from the inside. And for the washer method, we know that we have to integrate from this point up to this point, and we will place washers along this y-axis. So each washer will have a small depth of d of y. In terms of the y, we will look for something. Okay, the radius, outer radius minus the inner radius whole square into the d of y. We're going, of course, we have to place the washers from this point up to the this point where the two graphs meet each other. First, let's find out. So the first graph is y equals to plus minus 4 over under root x. If you take the square on both sides, we'll get y square equals to 4 over 4 square over x. And here we get x equals to 16 over y square. From the second one, we know x equals to 1. Just put these two together, equal to each other so that we can find the point of intersection. And here from here, we can just see y equals to plus minus 4. So this is actually minus 4 and this is plus 4. So we go from minus 4 up to the plus 4. Now the tricky part is to find the radius of this washer, the outer radius and the inner radius. In terms of the y, if you look at it, the outer radius, the bigger radius has been bounded by this curve, actually y equals to plus minus 4 over under root x, or we can just say in terms of the x 16 over y square. So let's write it down, minus 4 up to the 4 and 16 square over y square minus 1 square, that is x equals to 1. This is the lower limit, and then the whole thing pi comes out of the equation, and then d of y. If you try to solve this integral, you will find that there is some difficult part because this integral diverges, and we may not be able to use the washer method quite easily. So let's go for another method. We know there is a method of cylindrical shells, which is pretty straightforward, easy to use, and we will have no problems at all with this one. So for this one, we need to put shells. We start putting shells here. So let's put a shell from here to here. For the shell method, we have been placing the shells along the x-axis. So the distance between each of them will be very, very small, like the other shell that we'll put, the other shell we'll put. Let's call this d of x, and we'll be integrating like this. So for the method of shells, I just say shells. We'll be integrating, and for the method of shells, we know 2 pi, the radius of the shell and the height of the shell. These two things, that's it. If you know the radius of the shell, if you know the height of each shell, you're going to solve this integral quite easily. You can set it up very, very easily. And we definitely know that we have to put our shells from this point where actually the solid starts. Before that, everything goes hollow. So there's no point of taking anything here. So we are starting from x equals to 1, and we are going up to this point where x equals to 4. This is where the solid exists. This is where we have to put all of our cylinders, all of our shells there. So we are going to go from x equals to 1 to x equals to 4. Okay, simple. So 1 to 4, 2 pi. The radius of each shell. This is very easy because we are taking the y-axis as the axis of rotation. And when we place the shells in on the x-axis, the distance from the origin to that shell, which is the radius, it's just the x. It's just the point where we are placing the shells. So we have chosen different points on the x-axis, and wherever we place our shell gives us the radius, the distance between from the origin to that particular point. So I'm going to go with a different color for this. Let's use this one. So the radius is the distance from this point all up to this point where we have placed the shell, and we know we are placing it in x-axis, so the x will be the right thing to talk about the radius. In terms of the height, so in terms of the height, we are interested in this thing, and we know that this is the difference between the upper curve and the lower curve. So the upper curve minus lower curve gives us the height. Upper curve is plus 4 over under root x, minus the lower curve is minus 4 over under root x, and that's it. The rest is then just easy parts, simple calculations, a simple integral. Um, I won't solve, I won't do every step of it, but it is quite easy to do, and that becomes 8 x over under root x. X over under root x gives you the under root x, and you know under root x, the integral of under root x is x is to the power 1 over 2 plus 1 divided by 1 over 2 plus 1. You do all of these things and you get the answer 224. You put the limits pi over 3. That is the final answer. So please try it yourself and solve the integral, solve the definite integral. Let me know if you don't get this answer, and we will have a look at into your all of your work. So this is another question which has been taken from the fall 2021 final exams. This is quite interesting because you may get wrong in terms of the perception, initial perception that you make up out of this question. So let's solve this. First of all, we have a sphere. That's pretty easy. It's around sphere, okay, and the radius is 2 feet. So the distance between here to here is just 2 feet. And now we are having a bore. We are drilling it. Let's do it with another color. and we drill something like this out of it. And this is the interesting part. So if you look at this one, you might say this is a cylinder, and we know what is the volume of a cylinder, and you calculate it, and you might do it wrong, or maybe you go for the washer or for the you go for the like shell method to find the volume of this cylinder, because this is the actual part which has been taken out, and you might go wrong with it, because the thing is that there is a round top, a dome like structure on at the top and on the bottom as well. So this structure has been taken out. Okay, and we need to find the volume of all of this, which has been taken out from this sphere of radius 2 feet. So there are two methods which we can solve for this. I'm going to go for both. You can choose any, whatever you like. The idea is to show you that any problem can be solved with multiple methods, and you can just try different things if you're not sure, and you can just see whatever you can solve easily. So the thing is that we are interested to find the volume of something like this, which has been taken out of the sphere. Let me draw this again. So to find the volume, we can easily see that this can be divided into three parts. The one, this, 1, 2, and 3. The middle one is the cylinder, and the second one and the third one. And all around it, it's a sphere of radius 2. Let's talk about the volume of the cylinder in the middle. In the middle, I would say. So I would write down the cylinder equals to, we know the volume of a cylinder is the pi r square times the height. So what's the radius? We know this has been given here, that the radius was under root 3 square times the height. What is the height of this object? If we look at this one, this is the center, and we know the distance from here to here is under root 3. And we also know that distance from here to any point in the circle, this is going the circle. Sorry, like if I have not drawn it properly, but the distance from here to here is 2 feet. So you can easily find out this distance. Let's call it d. Okay, so d is the perpendicular distance. From the Pythagoras theorem, we can just say the hypotenuse square minus the base square, which is under root 3, and we're gonna get 1 here. And the total height is the upper one plus the lower one, which is this d and d. They both will be the same, so that becomes the height is equals to 2, height equals to 2, and we get 6 pi feet cubic feet from here. This is the volume of the cylinder. What is the volume of the upper dome? Now that is also interesting. Adjusted part, something round at the top. We can use the disk method. Let's place small disks here. One disk and another one disk, and the distance between the two disks is very small in terms of the y-axis. So we're gonna go with dy. Next disk and next disk. So this is the distance. Dy is the distance between these disks. So this is very small, dy. And we know from the method of disks, what is the volume of this whole object? That will be equal to pi r square. Sorry, dy. What is the limit? For where are we going? We are going from, okay, from this point to this point. We know that this point is 2, right? Because the whole radius, that was the whole point. The whole sphere was of radius 2 feet. And we know that the distance between the height from here to here was 1. So we have been left with now, we are going from 1 to 2 in terms of this. So we are going from 1 to 2. We are placing disks from y equals to 1 to y equals to 2, pi r square and everything, 1 and 2, pi. What is the radius of each disk? Like the distance between this point and this point. This distance has been limited by this circle. An equation of the circle of radius 2 will become x square plus y square equals to 2 square. In terms of y, it will become 2 square minus the y square. Okay. Or if I write down x equals to x square equals to 2 square minus y square, and then you can get x equals to under the root 2 square minus the y square. So that's it. You set up an integral for this. And once you solve this, you get an answer of 5 pi by 3. If you don't have calculator in the exams, or if it's not allowed, that's still fine. We can still find it. This is cubic feet. Now get back to the answer, to get back to the original question. So we have a cylinder, we have something at the top, something at the bottom, as a dome-like structure. We know the volume of each of these is pi, 5 pi by 3. Let's add them all this together. So the total volume will be equal to 6 pi cylinder plus the upper one, 5 pi by 3. And the lower one will be the same as the upper one, 5 pi by 3. And we get the answer of 28 pi by 3 cubic feet. That is our final answer. Another approach to solve these type of questions is that okay, let's go for this. Let's call this method 2. We have a sphere of radius 2. That's fine. We know that um, an object has been taken out of it, which is shaded here, and this is what we have been left with. This part on the right hand side, I would say right, and this part on the left hand side. Now we know that if we find out the volume of what has been left and we subtract it from the volume of the whole sphere, we're going to get this thing, the one in the middle, which has been removed from the sphere. So the volume of the sphere is from geometry 4 over 3 pi r cube, 4 over 3 by the radius 2 feet. We will get 33.5 cubic feet, the volume of the whole sphere. What has been left is this one, okay, on the left side and on the right hand side. And you can see that it is symmetric about the x-axis as well. So let's use the method of shells. You can use any method. Okay, let's talk about this as well. We can use washer method for this as well. You can see that there's a washer here. If you put some solid like here, okay, and it is empty in the middle, and then so this is a kind of a washer you can see here. So we place the washers, and then the distance between one washer and another one in terms of the y-axis is very small, like dy. And from the washer method, you can solve it. But I'm going to go with the cylindrical shells method because it is much easier to solve and very straightforward. So let's start putting shells. I'm going to go place one shell here. Yes, I know that I have left the bottom one because we will just find the volume of the upper one and we will just multiply by 2 to get the whole volume of the upper plus the lower one. For the upper one, we have placed a shell here. For the we know for the volume of the shell method, we have just done it in the last example. That is equals to 2 pi and the radius of the shell and the height of the shell. And we are placing it on the x-axis. So the distance between these two shells, like one shell and the other one, is very, very small, like dx. That will be the variable for the integration. That's it. What should be the limit of this integral? If we look closely, we know that the distance from this point to this point is under root 3. That was the board that was created. And our solid, which we are looking for, which exists now, starts from this point where x equals to under root 3. And it goes up to the last point here where x equals to 2, because it is a radius, it is a sphere of radius 2. So it is simple. We go from under root 3 to 2 pi. Again, the radius. This is very simple. We are looking for the distance from the basic y-axis, and we are placing shells on the x-axis. So wherever we place the shell, it is the radius. It becomes the radius. The distance from the origin to that point, which is just the x. Same as the previous example. That becomes the radius of this shell. So we are looking for the distance between from this point to this point. That's the radius. The height of the shell. The height of the shell, if you look at here, it is bounded below by this x-axis and bounded above by the equation of the circle. The circle is limiting our radius. So the radius becomes, in terms of the x, if I write down 4 minus x square, that comes from the same equation. We wrote it for the y square plus x square plus y square equals to 2 square. That comes from the same thing, d of x. And once you solve it, you get an answer of 2.1 cubic feet. We know this is only for the top one. For the bottom one, v total will be equal to 2 times this 2.1 because we have upper one, we have the lower one as well, like this. this one, and we get 4.2 cubic feet for this one. Now, if we subtract V of, I would say, bore equals to the total volume, which is 33.5 minus 4.2, which has been left, you're gonna get something similar to 28 pi over 3 cubic feet. The same answer as we got before with the different method. So it doesn't matter which method do you use, as long as you know what you're doing, how to do this, what kind of shape it will look like. The answer should be the same, and it shouldn't matter. Especially generally, if the question does not define any particular method, you can use any method. But if the question specifies any method, then you have to use it, because now the examiner wants to evaluate you on the basis of that particular method. It doesn't like, you won't get any marks if you solve it correctly using a different method, because the question specifies a method. For example, look at this question. This is also from some previous exams. I couldn't take the picture of that particular question, but I remember the statement and I used the same. So the area between the curves y equals to 2 and root x minus 1, y equals to x minus 1. These are the two curves. That gives you the area which is bounded by these two. And we rotate that area about the x equals to 6, that is a line. And this question specifies that you have to use the method of shells. You can't use any other method. Now, let's go for the solution. Let's plot this first. We know y equals to under root x. How does it look like? And this is x minus 1, so the graph will be shifted by 1 unit on the right hand side of the origin, and 2 multiplying it by 2 means that everything will become double, something like this. And the next line is y equals to x minus 1. Y equals to x is a line which passes through the origin. Y equals to x minus 1 will be something that will pass through x equals to 1. Okay, now we get this. So this curve is 2 under root x minus 1, which I plotted first, and this one is y equals to x minus 1. Good. We have where are they intersecting? We don't know. We're gonna find out in a bit. And now this is the axis of rotation. X equals to 6. This is interesting. We're gonna duplicate everything here. Let's replicate whatever we have done on the left hand side to the right hand side, and we will get something like this. So more or less it will becomes something like this. We have our solid object here, and has been rotated about the line x equals to 6, and we get this solid object. Definitely, we can use the method of the washer method as well, but the question specifies use method of shells, so we're gonna go for that. Let's change the color of the ink so you can understand. So we'll start placing the shells. Let's place one shell here. Okay, and using the volume of the shells, we know we have to go from some point to another 2 pi. We must be interested in the radius of the shell and the height of the shell. And now we are placing the shells on the x-axis, so the distance between each of them will be very small, because we are assuming infinite number of these shells, these cylinders. That's going to be small value of dx. We start putting shells from this point. Okay, so that will be the smallest shell that we'll put from here to here. Okay, so we are looking for x equals to 1 up to this point, where our solid stops, and there's nothing beyond that. So what is this point? Let's find out. We have two curves. Let's put them together. X minus 1 equals to x minus. If we take both of them equal to one another, we will find the point of intersection. This results in a quadratic equation of x squared minus 6x plus 5 equals to 0. If you solve that quadratic equation, you're going to get two roots, 1 and 5. That means that x equals to 1. At x equals to 1, they're going to intersect with each other, and the next point of intersection is x equals to 5, where they stop. So this is x equals to 5. We are going from 1 to 5 to pi. The radius, now we are not looking for something which starts from the origin up to our shell. Okay, we know this distance is at x, like we have done in the previous two examples. But the radius is this distance. We know that from the shells. We are placing shells, and this is the radius. The total distance from this point up to this point is 6. If you look closely, the radius is very simple, 6 minus x. The whole distance 6 minus this distance, which is x, and we're going to get the radius 6 minus x. The height of each shell. So this is the shell. It can't go below this point because there is nothing, there's no solid beyond that. So it cannot stop here and then this distance. So this is the height, h, which has been bounded, which is the upper curve minus the lower curve. So the upper curve is 2 root x minus 1, and the lower curve is just x minus 1 and d of x. Again, this results in a very simple integral. I leave it to you guys to solve it and let me know if you get the same answer, 272 pi divided by 15. So the main step is to set up the integral, and the rest is just using any technique. You have done like lots of techniques in chapter 8. I have another tutorial on chapter 8 as well. Please have a look at it if you want to revise some of those techniques, but this should be it. Now let's do another. The last example is from the exercise 6.5, in which we need to find the fluid force on one side of the semiconductor plate of radius 5 feet that rests vertically on its diameter at the bottom of a bowl filled with water to a depth of 6 feet. So one thing is clear, that we have a pool filled with fresh water, and the depth is 6 feet, and we have a semicircular plate of radius 5. You know that if we want to know the force, the formula is very simple. We go look for the weight density. Okay, so first of all, like we need to find the force which has been exerted by the fluid, by the water from the top. Definitely the force is being exerted from the top on all of these ones. Well, we just ignore. So we divide all of this object into small strips. This is one of these strip, okay, and then we place like infinite number of strips. We are putting them in on top of one another in terms of the y-axis. So the distance between each of them is very, very small. Let's call it d of y. And we will place our strips. So the last strip will be somewhat here. Okay. So we will be putting them. So one of the strip will be, let's say here. Okay. We are putting them when y equals to 0 up to the point where y equals to 5, because there's no strip on top of that. The whole semisphere ends at this x equals to y equals to 5. So we are going from y equals to 0 up to y equals to 5. We know what is the formula for the force. It equals to the liquid mass density times the strip depth or the strip height. Okay, it depends. So if you're going for the question which asks you to find the force which is due to immersing an object into a liquid, into water or something, so the force is exerted from the top. So we're always interested in the force which is being exerted from the top, and that should be this, that should depend on the depth of that strip of that object. In a similar question that we did in some of the questions we did in the lectures, we were trying to find out the force or the work done, which in terms of the questions in which we have to fill up a tank, and the water was was taken from the bottom of the ground, from the earth, and it was going upward to some water tank. In this case, the force is being exerted opposite to the gravity, and we will be interested in the height of the object of all of those strips, because the work is being done by taking something from the ground to a top. But in this case, we will be interested in the pressure which is being exerted by by the water on this submerged object. So we will be looking for the strip depth, not the height. And this is the good point to remember. And the last thing is the strip length. Okay, that is the last thing we need to know. Good. So let's set up the integral 0 to 5. We know the density of the fresh water is 62.4. It might not be given in the question, but you should remember this for the at least for the fresh water 62.4. The strip depth is again, let me change the color. Okay, so the depth is the distance from here to here. This is the depth. So we know that we are placing strips, okay, and the distance from the zero from x to zero to this point, this will be y, okay, and uh, depth, the depth is from here to here. This is the d. This from the surface of the water up to the point where the strip has been placed. This is the depth. So this is the depth, okay, and this is y, and the whole distance is 6 from y equals to 0 up to the 6 from the surface of the water to the bottom of the pool is total 6. So the depth becomes very easily, we can just see clearly 6 minus y. The whole thing 6. This distance is y, so the depth becomes 6 minus y times the strip length. So if we look for the strip length, this is the strip, and this is the circular object. So this length, let's call it distance d. It is starting from 0 and it's been limited by the circle, which has the equation for the 5 feet. We have x square plus y square equals to 5 square. So if we are writing everything in terms of y, so that means x will be equal to under root 5 square minus y square. So this is the distance from this point to this point. If you're looking for the whole length, that you need to multiply by 2. So the whole length will be equal to, so this is the distance, 2 times d, or 2 times x, or 2 times under root 5 square minus y square. So we get 2 times under root 5 square minus y square into dy. So that's it. This is setting up the integral, and if you solve this, you can get the answer 9502.6. This is the force in pounds. That's the final answer. Now, to solve this integral, it's not that easy. That's why maybe this question could be the part of an exam, because it requires a set of different skills to get to the final answer. The details will be discussed in chapter 8 about how to solve this integral that we have come up with this one, but I'll give you an idea. So let's see, 62.4 is a constant. It will come out of the whole integral. That is the 2. Okay, that's the constant. And in the middle, we will be left with 0 to 5. Okay, 6 minus y gets multiplied by this under the root. So you get 6, 5 square minus y square dy minus the other integral is 0 to 5. We have y 5 square minus y square dy. So you might remember from the chapter 8 that we can use the method of geometric substitution, in which you might have to use let's look at this table. The first one says if you see something under root a square minus x square where a is a constant, we use the substitution x equals to a sine theta. Then be ready that you're going to get dx equals to a cos theta into d theta. So we will have a cos theta because of the dx. Remember this thing because you will need it now. Okay, so you're gonna need it in terms of the dx, a different cos theta on this sine theta. Okay, let's go back. So we see here the x is the constant. It will come out with this one. Okay, so for this we're gonna go y equals to 5 times sine theta. If you do this substitution, I have like I said, for the tutorial of chapter 8, I've solved one question completely using this one, but you can try it yourself. If you put back y there, you're gonna get something 1 minus sine square under the root. So that will become 1 minus sine square theta. Okay, and the 5 will come out of the whole equation. You're going from 0 to 5. This dy will result in, like we've seen here, okay, a cos of theta. So that will become 5 cos of theta into d of theta. 1 minus sine square is an identity which results in cos square theta. the square will cancel with the under the root. You'll get a cos theta here. Cos theta multiplies with each other, and you're gonna get cos square theta inside this integral. And remember, whenever you get something like this, you use the double angle identity, 1 plus cos 2 theta divided by 2. When you solve this, I'm not going to do this, but I just give you a hint. So for the cos 2 theta, the integral will be sine 2 theta. This is the final answer. This is the answer after the integration. So you're going to go integral, okay, divided by 2. For this, again, you cannot do the back substitution because you know that y equals to 5 sine theta, or sine theta equals to y over 5, but you don't know what is sine 2 theta. You can't back substitute something easily like with sine 2 theta. So we have to use again the double angle identity, sine of theta and then cos of theta. Now you can do the back substitution because this is 2, the sine of theta we know here, y over 5. What about the cos theta? So for the cos theta, you have to use another thing. Again, from the basic identities, 1 minus sine square theta. And then you will kind of get the final answer. For this type of question, again, we see something under root 5 square minus y square, but we cannot, this is not the situation as this one, the first one. Why? Because there is a y, which is being multiplied by the whole under root thing. This one. Because of that, we cannot use the geometric substitution. If you try to use it, go ahead and you'll see the problem. You have gonna have like an integral which will have cos square and then with a sine multiplied by the sine, and things gonna go complicated. You may be able to solve it, but with a lot of difficulties. So we go for a normal substitution in which we let u equals to the 5 square minus y square, and that makes everything very easy. If you look at the d u, you're gonna get 2y, y is already there, so you will get minus 1 over 2y under the root u into d of u. Now minus 1 over 2 comes out as a constant. You know the integration of under root u, that will result in u raised to the power 1 over 2 plus 1 divided by 1 over 2 plus 1, and you're gonna solve it, everything. So once you do all of this, use the like the definite integral, and you're gonna get the answer 9502.6 pounds. So please try it yourself, and if you don't get these answers, let me check your work, and I'll help you with that. Thank you very much.